Well, I think one of the scenarios is the one regarding what our press release was about concerning T. Pyxidus. But I think that most scenarios now, for example, trying to account for the mass extinctions that have occurred throughout geological history, that for example, a gamma ray burst, a burst of gamma rays from a very massive star that collapses in on itself with the prompt formation of a black hole, and then with gamma ray jets that, if they're oriented just right, the gamma ray burst will be directed at Earth. These could be potentially devastating, the gamma ray bursts. In addition to that, there is a lot of debris in our solar system that was part of the fundamental building blocks of the solar system. Primordial matter, we call it, pristine chemical composition. There's been no chemical alteration. The comets are good examples of that. And some of the asteroids are very primitive. That is, they have a composition that is very pristine and primordial. It hasn't been altered by geological evolution. That is, they haven't been incorporated in large bodies that undergo geological evolution. So these are the basic building blocks. Well, these building blocks they're out there, and of course they can potentially collide with the planets, including Earth. And in fact, this is how we think the moon originated. The most widely held theory for the origin of the moon is the giant impactor theory, where billions of years ago, after Earth had developed an iron core, after it had, we call it differentiation, where the heavy elements sink to the center of a newly formed planet, and the lighter elements float to the surface because of their differing density. That Earth, once it differentiated, early in the history of the solar system, when the collisions with other bodies was more frequent, Earth was struck by a Mars-sized intruder body that then liquefied a large portion of Earth's mantle at the collision site and ejected this liquid rock out into space. This liquid rock then cooled and solidified and then reassembled itself by gravity. And that's what we have now, according to this theory, as the present-day moon. It eventually, and then suffered other collisions. The moon suffered other collisions. That gives the man in the moon appearance. The lunar seas, for example, those blue patches, are actually gigantic impact basins that have been flooded with lava, with liquid rock during lunar volcanism, during volcanic activity in lunar history. So these collisions happen much more frequently in the past, but that doesn't rule out that they can't happen now. So I think it's an area that is really deserving of a lot of exploration, as is being done now. Well, within the human lifespan, it's a very, very low probability. But on the other hand, one cannot rule it out. There are three families of asteroids that actually have the potential of colliding with Earth: the Amor asteroids, the Apollo asteroids, and the Aten asteroids. The Apollo asteroids actually have orbits that are internal to Earth's orbit, and they're perhaps the most likely, the Apollo asteroids, and those are being monitored very carefully by telescopic patrol observatories that have been set up. And if one of these Apollo asteroids were to enter into a collision course with Earth, hopefully we'd have enough warning. But we do, in fact, have the technology now and in the future to intercept and possibly deflect such a body. But during the span of a human lifetime, it's not likely. It's rather improbable that something large enough to do a great deal of devastation to the globe would happen. Now, there was an event in 1908, the Tunguska event, that appears to be a porous primitive asteroid that detonated, that exploded above the ground. And this leveled an entire forest in central Siberia near the Tunguska River. But fortunately, the area was very sparsely populated and there were no recorded human fatalities. But if that event had happened a few hours before, in other words, if it had happened if the detonation had happened over the ocean, that could have generated tidal waves, tsunamis, and that could have had a devastating effect on the coastlines. So it was really a lucky thing that the Tunguska event occurred over central Siberia and not over a populated area, like, for example, in Central and Western Europe. Well, I presume that our leadership would meet with NASA officials and plan to intercept such a body with either a kinetic energy device, a missile that would ram into it. But they would have to be very careful because you don't want to fragment it too much. And you don't want to fragment it in such a way that the fragments themselves would enhance the devastation. So you want to make sure it has to be carefully calculated. But I think this kind of a scenario has been anticipated, and I think that both with our space program, with other space programs, the Russian space program, the Chinese, I think there are plans for in case of such an event. I mean, and of course you would want to avoid worldwide panic and that kind of thing. So it's, I think the details remain to be seen, but such plans have been in the works. And in case of, for example, an Apollo asteroid being perturbed into a collision with us, with Earth. A Type 1a supernova is thought to be a white dwarf that undergoes total thermonuclear detonation. It explodes and completely obliterates itself, leaving no remnant. For example, we have yet to detect a neutron star or a black hole remnant of a Type 1a supernova explosion. It appears that the stellar explosion completely destroys the star. This explosion is extremely energetic. The amount of energy released is approximately 10 to the 51, 10 to the 52 ergs of energy. In other words, a Type 1a supernova can outshine the galaxy it's in, the entire galaxy, for a short time. And so they're extremely energetic. T Pyxidus is a recurrent nova, not a supernova, but a classical nova, but it recurs. Most classical novae we've seen only once. T Pyxidus has a classical nova explosion every roughly 20 years. And this continued from the early 1890s until 1967. So there were 5 nova explosions interspersed every roughly 20 years up until the 1967 explosion. Since 1967, this 20-year cycle has disappeared. Nothing has happened yet. In other words, it's 44 years overdue for the next thermonuclear explosion. What happens in a recurrent nova, and the reason I distinguish it from a supernova, is that a recurrent nova is a white dwarf. This is a star about the size of Earth, but it has an extremely high density. The density is 100 million grams in a cubic centimeter for a massive white dwarf. 100 million grams in a cubic centimeter, which means a thimbleful of this material would be hundreds of tons. If you weighed it here on Earth. What happens is the white dwarf is so dense that the electrons surrounding the nuclei have all been stripped away from the nuclei. And the electrons are actually forced to form a separate gas. We call it a degenerate electron gas. What happens is when you squeeze matter tighter and tighter, there's a principle in physics called the Pauli exclusion principle that states that no more than 2 electrons with opposite spins can occupy the same energy state. So what happens is when you squeeze matter tighter and tighter to higher and higher density, there are fewer and fewer energy states available to the electrons to occupy because all the lowest lying energy states are filled first. So an electron is forced to move very, very fast, and it can't slow down, it can't de-excite because the Pauli principle prevents it. And so what happens is these electrons move extremely fast, and as the density goes up, they move faster and faster, and that exerts pressure. Well, it's the pressure of these degenerate electrons, the degenerate electron gas, that prevents gravity from pulling this stuff in. But what happens is that as the white dwarf mass increases, there's an ultimate mass limit called the Chandrasekhar limit, beyond which a white dwarf cannot exist. Because at the Chandrasekhar limit, the degenerate electron gas pressure can no longer withstand the pull of gravity. It can no longer balance gravity and prevent the collapse of the white dwarf. Type 1a supernovae occur very close to the Chandrasekhar limit, when the white dwarf mass is very close to the Chandrasekhar limit. T Pyxidus has a white dwarf which is very close to the Chandrasekhar limit. Its presently determined mass fairly reliably well determined, is 1.37 solar masses. The Chandrasekhar limit for a carbon-oxygen white dwarf is 1.44 solar masses. So it doesn't have much more material to accumulate until it reaches the Chandrasekhar limit, in which case you'd have instantaneous collapse. But just before that happens, as the white dwarf grows in mass, the compressional heating, the weight of the material from the neighboring star, from its companion, presses down and raises the temperature high enough to detonate carbon, that is, to cause the carbon nuclei inside the white dwarf to fuse together, releasing energy. And so that is what we call a detonation. And that's the T Pyxidus, we believe, is very close to that point where a little bit more mass accreted onto the white dwarf will lead to so much heating that the temperature will rise to a few billion degrees, detonating carbon. But the carbon, when it ignites, when fusion ignites, it's explosive, because this weird gas, this degenerate electron gas, unlike an ideal gas like what the sun is made of or the air we breathe, where you heat it and it expands, the degenerate electron gas has no sensitivity to temperature, so it doesn't know it's being heated. In other words, the heat builds up, the nuclear reactions occur faster and faster and faster, but there's no compensating expansion to cool off. And so it's like a time bomb. Energy builds up very rapidly, and you get a tremendous thermonuclear explosion. That's a type 1a supernova. That is a classical nova takes place when the accreted hydrogen burns, but it burns in a degenerate region, and you get a classical nova explosion. That's about 10 to the 45 ergs of energy. It's a million times less energetic than a supernova. The supernova I'm talking about is the carbon nuclei, not the hydrogen, accreted hydrogen, but the carbon nuclei detonate, fuse together, and that's the type 1a supernova. That will happen to T Pyxidus when it reaches close to the Chandrasekhar limit. At the present rate of accretion that our modeling indicates for T Pyxidus, it will take another 10 million years, roughly 10 million years, to reach 1.44 solar masses. If the present mass of the white dwarf is 1.37 solar masses, and if the accretion rate that we've estimated from our accretion disk model fitting, from theoretical models of accretion disks, there's a pancake of matter surrounding the white dwarf, a pancake-shaped disk of gas we call an accretion disk. And that accretion disk is adding material to the white dwarf. But at the rate at which it's adding material to the white dwarf, it's going to be another 10 million years, roughly, before the Chandrasekhar limit is reached. As the interior, the core of the white dwarf becomes hotter and hotter due to the compression, and the temperature gets up into a few billion degrees, the ignition temperature of carbon will be reached. That is, carbon will be able to undergo carbon-on-carbon fusion with the release of energy. This will start out, according to supernova models that have been carried out in the last few years, this will start out as what we call a deflagration. A burning front will propagate, will move outward at subsonic speeds. But as this burning front moves out, eventually, very soon, it will turn into a supersonic burning front. You'll have a breakout of the shock wave or blast wave from this thermonuclear explosion. That breakout will produce a burst of gamma rays and hard X-rays, very high energy radiation for a few seconds. This radiation, if the supernova is close enough, this radiation could then affect Earth. In other words, you would have input of hard X-rays and gamma rays into our atmosphere. This could introduce chemical reactions producing a lot of nitrous oxides, which could then eventually destroy the ozone layer. I mean, that's the first thing you think about, is that if the ozone layer is destroyed, then the very high energy radiation is lethal to DNA. It would destroy the biosphere. But the supernova has to be close enough. Now, type 1a supernovae they're more common than type 2. The type 2 supernova, when the ordinary person thinks of a type 2 supernova, when the public thinks of a normal supernova, they think of a huge, massive star that collapses in on itself and produces a black hole or a pulsar at the center and then this high velocity expanding gas. That type of supernova, called a type 2 supernova, comes from very massive stars that are very luminous before they went supernova. They can be seen at great distances. What makes a type 1a supernova really unusual in that regard is that a white dwarf is very dim. And even white dwarfs in close binaries where mass transfer is going on, they're really very faint. You don't see them out to very long distances, and they're a more common type of star. And therefore, since they're more common and fainter, they really pose some reason to be concerned, because you don't see them as easily as more massive stars that are much more luminous. So I think the main thing that one might be concerned about is the input of high energy radiation into our atmosphere. But the supernova, if you go on the basis of type 2 supernovae, then the current estimates are that if the type 2 supernova is within roughly 30 light years, 30 or 40 light years or closer, then you'd really have massive input of high energy radiation. But that's for type 2 supernovae. And my collaborator, Dr. Patrick Godin at Villanova, just did a quick back-of-the-envelope calculation and determined that if you had within 1,000 parsecs a type 1a supernova go off, and if it was a low tilt such that the accretion disk and material didn't block the breakout of the blast wave, you would have a burst of gamma rays that would essentially be as bright as the sun. The estimate by Peter Huflick is that 10 to the 48 to 10 to the 50 ergs per second in hard X-rays and gamma rays would be emitted. So, and we don't know exactly how far away. We know that it's closer than 1,000 parsecs, but how much closer? Our best estimates right now are it could be, the models allow it to be even as close as 500 parsecs, but that may be too far for it to do real damage to Earth. But we're still working on this, and we're submitting a paper to the Astrophysical Journal Letters on this topic. I think the world would end if, leaving aside all these other catastrophes and leaving aside the possibility that they could completely destroy Earth, which is not clear. I think that the real end of Earth will take place when the sun, which is now a very average star on what we call the main sequence stage of evolution, when the sun runs out of hydrogen in its core. It's building up helium right now. When this happens, the sun will drastically change its structure. When it uses up hydrogen, it no longer has thermonuclear fusion energy to provide its luminosity. In other words, it's shining because of thermonuclear fusion of hydrogen into helium. When that hydrogen fuel source runs out, the sun will drastically change its structure and evolve into what we call a red giant star. A red giant star is one like, for example, you may be familiar with Antares, which is the brightest star in the constellation Scorpius. It's a very red star. It's a red supergiant star. Another example is Betelgeuse in the constellation Orion, famous wintertime constellation here in the northern hemisphere. These stars, these red supergiants, for example, Antares, if you placed it where the sun is located, our orbit would be inside of that star. So I think the ultimate end of the Earth is going to be when the sun expands to a red giant. Its outer layers swell up to beyond 93 million miles. Earth will then start to experience viscous drag as it orbits the red giant sun. This viscous drag will cause the orbit of Earth to decay, much like an artificial satellite that we launch around Earth will eventually burn up in the atmosphere. Earth will eventually be incinerated inside the sun. Mercury, Venus, and Earth, and possibly Mars, will undergo what we call death spirals. Their orbits will decay. As they lose orbital angular momentum due to the viscous drag, they will decay and spiral into the sun, where they encounter very high temperatures, and essentially Earth will vaporize. Now, this won't happen for at least the sun has approximately 5.4 billion more years as a main sequence star, then a few 100 million years beyond that. So I would say in roughly 6 billion years from now, the inner planets should be engulfed by the red giant sun. But by then, presumably advanced life here on Earth will have colonized other worlds, and so we don't have to worry about it. But I think that's perhaps the best answer to your question, is that eventually it's got to happen. The sun will become a red giant star, and the inner planets will then decay and burn up inside the sun, vaporize, and then Jupiter will start to accumulate mass. And if Jupiter accumulates more hydrogen-rich gas than its present mass, its present mass is 1/1000th the sun's mass. If Jupiter accretes about 10, I would say roughly, it reaches 10 times its present mass, and it could do this by sweeping up solar gas as it orbits the sun, or the future red giant sun. It could undergo a thermonuclear ignition and become a star, and so you'd have the sun and Jupiter as a binary system. But this is, of course, something that is billions of years into the future.